Thank you for introducing me. Today I will be talking about our recently developed fully quantum mechanical approach to proton-hydrogen scattering problem. Our research in charge exchange reactions occurring in ion atom collisions has started not long ago. For this reason, my talk is about the simplest prototype of such reactions. However, we have a full capacity to further develop our approach for more complicated atomic and molecular targets. Our research for anti-proton projectile scattering from those targets has been published in several papers, and this supports this statement. So this work has been done together with Alicia Kadyrov, Sanat Aladbayev, and Igor Bray. We are from Curtin University, which is located in Western Australia. So the proton-hydrogen scattering problem has been attracting the attention of theoretical physicists and experimentalists for several decades now. And what's surprising, despite this is the simplest three-body problem, there still exists discrepancies between theory and experiment for the total ionization cross-section. And in addition, the discrepancy is mainly at intermediate energies, where the theoretical approach, the results of theoretical approach are higher than the experimental measurements. In addition, to our knowledge, all available approaches are either based on semi-classical close coupling formalism or the first order iterative approaches. So no fully quantum mechanical approach is available which would cover whole energy range. So let's have a look at the process when proton collides with atomic hydrogen. So during the collision, the following processes can be initiated: elastic scattering, when the projectile scatters off the target without losing energy; excitation, when the projectile excites the target electron to its higher bound state; ionization, when the projectile knocks off the electron, and there is also a possibility for the projectile to capture the target electron. And the fact that the projectile can form a bound state with the target electron brings additional complexities. And here, to be able to accurately calculate all these aforementioned processes, we need to be dealing with the two-center expansion of total scattering wave function, which I will be talking about in this slide. So let me introduce our approach. So we start from the exact time-independent Schrödinger equation for the total scattering wave function. For the sake of theoretical derivations, it's best to utilize the Jacobian coordinates. And the most natural way to build up the total scattering wave function is to expand it around each nuclear center here, and here FA functions carry information about the elastic scattering of the target and excitation of the target, plus the ionization which is coming from the target side, and the FB functions carries information about the electron capture processes, and also the second part of the ionization which is coming from the projectile center. Here phi alpha and phi beta are the pseudostates of atomic hydrogen, and they are formed as a linear combination of orthogonal Laguerre functions. And if we increase the number of pseudostates on each center, we'll get a better description of two-center three-body system. This will allow us to increase the accuracy of all cross-sections for all undergoing processes. So if we insert the total scattering wave function into the Schrödinger equation, after some algebra we will derive the Lippmann-Schwinder equations, which is in the momentum space, and there is offshore integration. So conventional methods to solve this equation is to discretize the offshore integration into many quadratic points, and then convert these integral equations to the set of linear equations. The size of linear equations is the total number of channels multiplied by the number of quadratic points. and this number can easily become over 100,000, and one need to be using the scale effect routines across many computing nodes, and also on top of that, too many matrix elements needs to be calculated. This will overall make the method very small and computationally demanding. So we have developed a new approach where we express V and T matrices in a form where the offshore momentum dependent parts are factored out. So if we insert V and T defined this way into the integral term of the Liebman-Schwinger equations, and then combine the offshore dependent part together with the Green function, it will look like this, and the contour offshore integration can be evaluated analytically if we use the residue theorem from the complex analysis, and if we bring these results back to the Liebman-Schwinger equation, we will get a new set of scattering equations. Unlike the original Liebman-Schwinger equations, which were in the momentum space, this one is in the configuration space. And at the first glance, one would think, what's the advantage of these integral equations over the original integral equations? But after careful analysis, one can figure out that these steps can be solved using much simpler methods. So this is because the upper limit of integration is a point where we have to find the T matrix. So we can use this fact in our solving strategy. So we initialize the solution at a point where V and T matrices are exactly zero. This is very distant point before the collision, and then we choose some appropriate rules for the integral and propagate the solution to the next step, and this process will be repeated until we reach the point where the solution T matrix is again infinitely small. After this procedure, we will get the T matrix at the entire significant space range, and this will allow us to calculate electron distribution at any coordinate point. The old method was not capable of that. So once we find the T matrix, we can calculate the cross section for any particular transitions that we are interested in, and all transitions into continuous states altogether make up total ionization cross sections.
May I ask you a question? Why are you using back parameter but not partial wave expansion? If you would like full equatorial approach, you back parameter good, but for some energy it doesn't work well. Yeah. Why not a partial wave extension?
No, in this case, the impact parameter is not the same as in semi-classical approaches. It's just mathematical transformation from momentum space to new space by simple Fourier transformation. It means
that you have a z component and
yes,
rho
component and rho.
Just a variable, variable.
We don't have any straight line approximation for the project. Yeah. So to test our approach and to check its validity and performance, we have done calculations for anti-proton-hydrogen collisions, and for this collision system we have results which were obtained using old method based on quadrature discretization. As you see, we've got a very good agreement between two methods, and in addition the time spent for the new method was 3 orders of magnitude less than the time spent for the old method. This is very encouraging. So after having done all necessary tests, we now looking at the two-center proton-hydrogen collisions. As I mentioned above, the most natural way to approach this problem is to use two-center total scattering wave functions, and it's best to use the same number of pseudostates on each center. In this context, the following fact can be useful. So there were several papers indicating that two-center symmetric calculations have some ill conditioning problems, and one of them is PRA by Toshima. He explicitly states that two-center close coupling formalism possesses inherent ill conditioning when we use pseudo-continuous states on each centers. To overcome these difficulties, we need to meet the following requirements should be met. So our matrix elements needs to be extremely accurate. So for this purpose, we used we derived all our matrix elements fully analytically, and we used the arbitrary precision package. Also, another thing that we need to be concerned about is the accuracy of the propagation. For this purpose, we use the step size doubling and halving technique, and also the basis size on each center should be large enough, so the scattering wave function built from small number of pseudo states cannot describe the three-body system accurately, so it needs to be large enough. And the last thing, we need to always keep an eye on the unitarity conservation. So this is a good plot to explain how our close coupling approach works. So this is the plot for the normalization of the total scattering wave function at different positions of the projectile from the target. And ideally, this normalization should always be 1 at all points, but this is the for lowest calculated energy and for lowest impact parameter, and this is the most severe case where the unitarity issues, where the ill conditioning issues is most severe. So as you see, when we have our base is small, the deviation from unity is almost 60%, but as we increase our basis size, it decreases, and so we have a good handle here to control everything. So in this plot, we show the time energy dependence of the total electron capture cross section. As you see, we've got a very good agreement at all calculated energies with the experiment. And also theoretical calculations of winter, and they are also in good agreement. At energies below 10 keV, the ill conditioning issues are more severe, so it's just it makes our calculations a little bit slower. The calculations are still running. We will report them later. So this is our result for the time energy dependence of the total ionization cross sections, and surprisingly, we are getting some disagreement with the experiment at intermediate energy. Why I am saying surprising is because this is close coupling approach, and everything is convergent here. So for electron capture processes, we are getting perfect agreement, and because of this is close coupling approach, it should produce perfect agreement for these cross sections too. But we don't see this. It's a bit puzzling for us. Maybe it's a good idea to revisit the experiment at this small energy region, because the calculations of other theories are also higher here. And this is the cross sections for the electron capture into the 2s state of the projectile. We are getting overall good agreement at all energies, and also there is an agreement with semi-classical close coupling approach here too. This is the cross section for the electron capture into 2p level of the projectile. At very low energies there is a good agreement, but as the energy goes up, we see some disagreement, but the sharp decay, we see also sharp decay of the total of the capture cross section, which is characteristic to all electron capture processes. And I wanted to draw your attention to the fact this is the transitions into the state with L equal to 1, and for this reason these calculations are made with maximum allowed angular momentum 2, And probably for this particular cross-section, we may further improve our results if we increase maximum allowed angular momentum. This is not final results, so we're still working on this, so it's not published yet. And this is our results for the excitation of the hydrogen target into the 2s level. So it has been studied experimentally studied on 3 occasions, and there are disagreement between different experiments themselves, and they have quite a large error bars. So in this sense, we may say that we are getting some reasonable agreement at all energies. And this is the cross-section for the excitation of atomic hydrogen into 2p level. So it's again the transition into the state with L equal to 1, and maybe here we are getting good agreement, but at higher energies our results are systematically lower. Probably we can further improve this data by increasing maximum allowed angular momentum. And let me spend a few minutes talking about how this current research can be helpful for the astrophysics. So in 1996, the observations from Hiyaki comment bring some surprises to astrophysical community. Before that time, nobody expected significant X-ray emissions coming from cometary environment. But later, when Chandra observatory was up in orbit, it was established that the origin of such X-ray emission was the charge exchange reactions occurring when the solar wind ions interact with the cometary environment. So they produce lots of reactions where charge exchange are important. So our task should be to provide accurate cross-sections for the reactions where the charge exchange reactions are important. So at the moment we have done calculations only for proton-hydrogen collisions, but we have a capacity to do calculations for hydrogen, helium atom, lithium, sodium, and all inert gases, also molecular targets such as H2+, H2 and water molecule. And also we have all ingredients to do calculations for argon 18 plus argon collisions, for which the measurements of Berlin Ebbing collaborations are available. We have a very good structure model for argon target. For anti-proton projectiles, we are getting very good agreement with experiments for these targets. So it shouldn't be very difficult to generalize the proton projectiles. So to conclude this talk, I would like to emphasize again, we have developed a new fluid quantum mechanical approach, and for the first time we did the integral over optical momentum in the deep machine equations were calculated fully analytically. So our calculated cross-sections for various processes are overall in good agreement with the experiment. So, and few words about our future plans. So we are ready to perform calculations for these targets where for anti-proton projectiles we get good results. And lastly, I would like to thank again organizers, and I would like to I'm thankful to Curtin University for providing a pleasant environment to carry on this research. Center of Excellence for Antimatter and Matter Studies, which does not exist any longer, but we were getting financial support last years, and also computing facilities such as NCI and IREC, which allowed us some computational time for our calculations. Thank you very much for your attention.